Hello again. So this is part 3 of the third video. Structural analysis made fun and easy with a single span beam with two small cantilevers equal, symmetrical. These three videos are all about loading, bending moments and stresses. Please like the video and subscribe to the channel. So basically it's this is the continuation, a completion of the problem. I've been through how we got the maximum moments. In the previous videos we worked out the loading on the beam, the moments at the support and the hogging moment in the midspan, and then we started looking at the stresses that will be generated on the section. So now we're moving on to finishing the problem. So section AA, this is the cross section that's provided in the question, and it's given that Ixx equals 42.26 times 10 to the power 6 millimeters 4 and Y equals 59.1. So basically it's a U-shaped section, 250 wide, 200 millimeters high. Now, got to be honest. Oh yeah, neutral axis is at 59.1 millimeters above the bottom. So the distance from the neutral axis to the top is 160.9 millimeters. I've got to be honest and say they show that the width of the webs are 15 millimeters wide, but I'm not sure why they're showing 15 millimeters wide. So if I can find that out, I haven't used that dimension in the calculations. So I'm going to it's given, this second moment of area is given, but I'll do a bonus video on how to calculate the neutral axis and second moment of area on this section manually. But obviously you wouldn't do that in the exam, but I just do it out of interest so that people can see how they get these values. So first of all, we know that the allowable bending stress in tension is 30 newtons per millimeter squared, and the allowable compression stress is 17 newton millimeter squared. So as per the previous videos, let's start at the maximum hogging at the support. So in that case, it's going to be tension over the support where the beam is cantilevering over. The moment's going to be at the top. So the tension stress, as I've drawn in red, tension will be in red. And we've got to make sure that this value is less than 30 newton per millimeter squared at the top, otherwise the section will fail. So we know the maximum tension at the top of the section at the support hogging moment must be equal to or less than 30 newtons per millimeter. So we know that compression stress can be equal to or less than 17 newton millimeters. Now I'm telling you, because I know the answer to this, that because of the shape of the section, basically the compression stress is going to be low because there's a lot of mass. The area of the section along here is large, whereas you've just got the two legs at the bottom. So obviously the area of the section at the top is less than the bottom. So that means the stress is going to be higher in these legs, where you've got a big fat section there. They can soak up. They can provide a lot of stress in that area. So let's do basically the calculation. So this is the engineer's theory of bending stresses. Sigma xx equals mxx times the distance y up and down the y-axis divided by the second moment of area xx. So as per above, at the top for tension y, distance y is 200 minus 59.1 is 140.9. Oh yeah, sorry. So that is 140. Correction. So the distance from there to there is 140.9. That distance is 200. The distance from the neutral axis to the base of the section is 59.1. So we put those values into this, we get sigma xx, and we've already found that the moment was 0.5 W, and that was kilonewtons per meter. So it's 0.5 W times 10 to the power 6 times 140.9 millimeters divided by the Ixx of the section, which is given as 42.26 times 10 to the power of 6. So this time we're working it the other way around, because we got the allowable stress is 30. We want to confirm what W is. We need to find what that value of W is. It's going to be, the moment is 0.5 W, so we need to find out what W is. So we do 30 equals 0.5 W times a million, which is 10 to the power of 6, times 140.9 divided by 42.26 times 10 times a million. So the millions cancel out there, rearranged in this equation. 0.5 W equals 30 times I, so the I goes to this side, the top, and then that goes underneath, which is 30 times 42.26 times 10 to the power of 6 divided by 140.9. That is 0.5 W. That value is 8.99789. So it's basically 9. 0.5 W is 9. So W is 9 divided by 2, which is 18 kilonewtons per meter. So now we need to check that. Just double checking I've got all the calculations for that correct. So let's put that back in. Sigma XX equals 0.5 times 18 times a million times 140.9 divided by 42.46 times a million, and that's 30.007 newtons per millimeter squared. So that 18 was correct. So that means that the tension at the top will be 30 newtons per millimeter squared if W is 18 kilonewtons per meter. So now we need to check the compression stress generated at the bottom doesn't exceed 70 at the support. So the distance to the bottom of the section is 59.1. On the diagram again, it's from here to here, that's 59.1. So we got to put that in the section, we got to put that in the equation. Sorry, I went past it. So we need to check the compression. So the compression stress is 0.5 times 18 times 10 to the power of 6 times 59.1 divided by second moment of area, and that gives us 12.58 newtons per millimeter squared. So that's well under 70. So basically what this shows us is that the tension stress limits the moment capacity of the section at the support, because the compression stress is much less. It shows that the tension stress limits the moment capacity of the section, not the compression stress, as the compression stress should be much lower. It's because of the shape of the section, as I was saying. The shape of the section, there's a big area at the bottom, so that's going to have more stress. That can take more stress. And it's because basically the neutral axis is depending on the center of area of the section. So when you've got a big section of area at the bottom, that means the neutral axis goes down. So in the calculation, for the compression, you've got exactly the same as the tension equation, except it's 59.1. So it's not as 140 is double the distance to the top. So the stress is the tension stress at the top is more than 2 times the tension. More than 2 times the compression stress at the bottom. So so at the moment, so that's fine. So that means that at the moment, based on the support check only, we could apply W equals 18 kilonewtons per meter. So now we need to check the next biggest stress, bending stress, that's at the middle. So the maximum sagging at the midspan, we already worked out in the last video, is 1.5 times W, which is a UDL. The maximum tension, and this time it's at the bottom because it's sagging, so that means it's going to try and crack at the bottom. It's going to crush at the top and crack at the bottom. Just got to remember that, crack at the top and crack at the bottom and crush at the top. So again, we used engineer's theory of bending stresses. Sigma xx equals mxx times distance divided by second moment of area. Now, so for the top, for the tension at the bottom, this time y is 59.1 because the tension is at the bottom. So 1.5 W, that's the moment that we calculated from the last video, times a million, times 59.1 divided by 42.26 times a million. So the millions cancel out, so it's 1.5 W times 59.1 divided by 42.26 equals the stress. That's the tension at the bottom. We got to limit the tension at the bottom to 30, so 30 equals 1.5 times a million times 59.1 divided by 42.26 times a million. So if we rearrange that, we've got to take the I to this side and then divide by the Y. 1.5 Y times a million equals 30 times 42.26 times a million divided by 59.1. That means that 1.5 W is 21.452. So W equals 21.452 divided by 1.5. That gives us W equals 14.3. So at the moment, we think that W needs to be reduced from, it could have been 18 for the support, but now we're saying it needs to be 14 because the tension stress in the sagging is going to be bigger. When you think about it, we had 4 meter span. We're going to get more stress in the middle than at the support because the support moment's 60. The support moment is 0.5 W and the sagging moment's 1.5. So the sagging moment's 3 times bigger as the support moment. So as before, we need to now check the compression stress generated is less than 70 because that's in the question. So we do the same equation. The y distance for the compression is now 140.6 because it's from the neutral axis to the top is 140.9. So then that means that we got sigma xx equals 1.5 times 14.3 because W we found for tension is 14.3 times 140.9 divided by 42.26. So that gives us 71.52. So that's not okay because we need the compression stress to be limited to 70. Which is not far out, it's only 1.52 newtons per millimeter squared out. So we just try a little bit, let's try a little bit less of W. Instead of having W 14.3, let's try 13.8. So when we try that, I get the stress of 69.0163, blah, blah, blah. So that's a little bit under. So let's try 13.99 and put that into this equation, and then you get 69.9665. So that's basically 70. That's more or less 70. So we're saying it's 14, basically 14 kilonewtons per meter. And that could be coincidence, but hoping that the examination has said that was the answer because it's a nice round number. So basically the answer, so the safe W load over the whole beam is 14, because then that gives you less than 30 tension at the top at the support, less than 70 at the bottom at the support, less than 70 compression at the middle, less than 30 tension at the middle. So this problem, as well as solving the answer, is good experience because this has been a good demonstration. It shows that this section is not symmetrical, so we get different stresses at the top and the bottom for the same moment. If we had a symmetrical section, we had one moment, then the y value would be the same from top and bottom, but it's different. So we get much bigger compression stress at the top section as a result of the tension at the bottom, and vice versa. So we get because we've got at the middle we've got tension of 30 at the bottom of the section and we get 70 at the top, so that's more than double the tension stress. So this is a good example. So we had to reduce W a little bit. We had to reduce W to suit the sagging condition because that's controlling it. So basically that's the solution to the entire problem. I'm going to do a bonus video on that, working out the second moment of area on the neutral axis. That's just to prove that how you can do it easy. You wouldn't need to do that in the exam, but so there's another video from Structural Analysis Made Fun and Easy. Please like this video and subscribe to the channel. And any questions or comments, please just put them underneath. But that concludes this question. Thanks for watching.